And we're back. We were talking about indeterminate forms and L'Hopital's rule. So here's the list of indeterminate forms I gave you. We went over what to do with these two. Let's move on to this one. So we can't use L'Hopital's rule directly to 0 times infinity. L'Hopital's rule is only directly useful for any of these. But so here's what we do. So again, what this means is that we're doing a limit and say I'm multiplying two functions together and one of them goes to 0 and the other one goes to infinity. So maybe f of x goes to 0 and g of x goes to infinity, or it could be the other way around. All we're going to do is use a simple algebra trick to sort of artificially turn this into one of these two, and then we would use L'Hopital's rule. So instead of doing f of x times g of x, I'm doing f of x divided by 1 over g of x. And this is either going to be 0 over 0 or infinity over infinity. For example, if f of x was the one that went to 0 and g of x was the one that went to infinity, then the top here is going to 0 and the bottom is like 1 over infinity, which is 0. So this turns into a 0 over 0 form. Of course, f of x and g of x are sort of interchangeable here. I mean, not exactly, because one of them goes to 0 and the other one goes to infinity. But they're interchangeable in the sense that it doesn't matter too much which one goes to 0 and which one goes to infinity. And it also doesn't matter which one I choose to put on the bottom. I could leave g of x on the top and put 1 over f of x on the bottom. For example, how about this? X squared e to the minus x. Of course, e to the x looks like this. So if x is going to infinity, like this is like e to the minus infinity. In other words, it's like this graph, but I'm going off to the left. So this goes to 0. Meanwhile, of course, x goes to infinity, so x squared also goes to infinity. So this is a infinity times 0 form. So let's do this. I'm going to throw one of these on the bottom. I don't want to deal with, like, if I put x squared on the bottom, like the reciprocal of x squared is x to the minus 2, I would rather deal with positive powers of x. So I'm going to leave x squared on the top, and on the bottom I'm going to put the reciprocal of e to the minus x, like 1 over e to the minus x, which is e to the positive x. Now, as we promised, the new thing is something that L'Hopital's rule applies to. In this case, the top is going to infinity and the bottom is going to infinity. Like, as x goes to positive infinity, I'm looking at this graph as I go farther to the right, so this is going up and up and up. So this is an infinity over infinity form. So I do L'Hopital's rule. Derivative is 2x. This is just e to the x. Now I look at it again. This is still infinity over infinity form. So let's go again. Now the top is just 2. Derivative of 2x is 2. And then e to the x is still just e to the x. Okay, hopefully we don't have to do this forever. So I look at the new limit. The top is no longer going to infinity. The top is just 2. The bottom is still going to infinity, but this is not an indeterminate form anymore. If I have a fixed number and I'm dividing it by something that goes to infinity, that's just 0. Okay, so that's an infinity times 0 form. Let's learn how to do more of these. I'm going to lump the next 3 together because the advice is the same. These are all dealing with powers. Like I've got f of x to the g of x power. Like if I write 0 over 0, that means I'm doing a function f of x that goes to 0 raised to the power of a function g of x that also goes to 0. So what do we do here? So I'm doing some function raised to the power of some other function, and I'm going to call this limit L. The trick is I'm going to do the natural log of both sides. And natural log is a continuous function, so I can take the natural log inside there. And why am I doing this? I'm going to use a natural log rule, which allows me to take a power and put it in front. So I get g of x times ln f of x. This new limit should always be a 0 times infinity form. And it depends which case you're in, because there's 3 possibilities. Either f of x and g of x are both going to 0, or f is going to infinity and g is going to 0, or it's like this. And so which one of these things is going to 0 and which one's going to infinity depends on what case you're in. But one of these things, whether it's g of x or ln f of x, one of them is going to 0 and the other one's going to infinity. And we already learned what to do when you have an infinity times 0 form. So that's how these go. Let's do one. So I'm doing the limit as x goes to 0 from the right, and by the way, L'Hopital's rule is fine. You can go from the left or the right, or with neither direction specified. So this will be fine. But the point is I'm doing x to the x power, and x is going to 0. So this is a 0 to the 0 form. So we're going to call that L. I do the natural log. Of course, this comes down. So this is x ln x. Great. And now this new limit is supposed to be, well, I guess in this case, x is going to 0, so this one's going to 0. ln x, as x goes to 0, let me just draw a little not so great picture of the graph of ln x just to jog your memory. Actually, natural log is the inverse function of e to the x. I just drew that a second ago. So the graph is really just a reflection. It's like this. It's like a sideways version. We're doing the limit as x goes to 0 from the right, which is this vertical asymptote. So this is going to negative infinity, and like we said just a second ago, this is going to 0. So I call this a 0 times infinity form, and again, I don't differentiate between infinity and negative infinity in this context. Okay, so what do we do with 0 times infinity? I turn this into a fraction, because L'Hopital's rule is good for fractions. It's either 0 over 0 or infinity over infinity. So I have an option of like which one do I want to throw on the bottom. I don't think I want to make a fraction with x on the top and 1 over ln x on the bottom. That sounds like it might be overly complicated. Let me leave ln x on top, and then the reciprocal of x would be x to the minus 1. I like that because I'm about to do the derivative of the top and the bottom, and it's not so much that I like x to the minus 1, but I like leaving the ln x here because the derivative of ln x is simpler. So, alright, I'm about to use L'Hopital's rule, but let me justify it first. This is, I had a better red pen. Yeah, here we go. This is, so x is going to 0 from the right. As we talked about, ln x goes to negative infinity, but when we're in this context, I'll just write infinity. X to the minus 1, as x goes to 0, this is like 1 over 0, which we call infinity. So this is an infinity over infinity form. So we are justified using L'Hopital's rule. So let's do it. Derivative of ln x is 1 over x. Derivative of x to the minus 1 is minus 1x to the minus 2. That's how I do derivatives of powers. Okay. So now I have this to look at, and I should probably just clean it up. So what do we have here? This will give me a negative sign. I've got 1 over x, and then an x to the minus 2 in the bottom. That's like multiplying by x squared. So I can cancel. So I just get negative x. And now looking at this, this is easy. X is going to 0, so I just get 0. Now, when you do this, there's one thing that's hard to remember because I really want to celebrate because we're basically done, but actually we're not quite done. We were supposed to find this original limit L, and what I actually just found is the natural log of L. So natural log of L is 0. That means to solve for L, I do e to both sides. So L is actually e to the 0, which is 1. That's my answer. It's really easy to forget to do that last part, but if you're doing this trick where you find ln L, you have to remember that whatever you get, you have to do e to that power in the end. Okay. Let's do another one. This is a 1 to the infinity form. X is going to infinity, so the thing in parentheses, 1 over x is going to 0, so this is going to 1. And meanwhile, the power that I'm raising it to is going to infinity. So this is what we call a 1 to the infinity form. But the basic strategy for attacking these is all the same. Like we just did a 0 to the 0, but 1 to the infinity is all, like it's the same strategy. It's going to be the thing where I find natural log L. All right. So let me sneak this in there. So we're going to call this L. Let's find natural log L. So it's like that. This comes down. So we're there. Okay. The result should be a 0 times infinity form. And sure enough, x is going to infinity. This part is going to, well, ln of 1, which is 0, so this one's going to infinity, this one's going to 0. So we're like that. So I'm going to turn this into a fraction somehow. I'm going to pick one of these two things and put the reciprocal of it on the bottom. And I'm going to put the x on the bottom. This part is complicated enough. The reciprocal of it would be even worse. So I think my best option is to stick the x on the bottom. And in fact, okay, let me strategically start writing x to the minus 1 instead of this 1 over x. Because I am about to use L'Hopital's rule, and that means I'm going to use derivatives, and it's going to be easier to do the derivative of x to the minus 1, looking at it that way. So what was I doing? I was putting the x on the bottom, and so, well, I mean, the reciprocal of x on the bottom, so I'm there. Okay. Now, as x goes to infinity, this goes to 0, and this goes to 0, so the bottom's going to 0, and the top is again, it's like natural log 1, which is 0. So this is a 0 over 0 form. So I am justified using L'Hopital's rule. So I'm doing the derivative of the top and the bottom. Okay, bottom's easier. So I'm like that. Okay, derivative of the top. I need the chain rule. So the derivative of natural log is 1 over x. I'm going to do 1 over that. And sorry, let me just kind of make some space in between this line and the next line, just so it's clear what's going on. What was I doing? I was doing the chain rule. So this turns into this, but I need to multiply by the derivative of the inside. So I multiply by the derivative of 1 plus x to the minus 1. This 1 just disappears when I do the derivative, and the derivative of x to the minus 1 is minus 1 x to the minus 2. So I'm there. And now let me clean this up. In particular, bam, that makes me happy. And now I look at this again, x is going to infinity, x to the minus 1, that's the same as 1 over x, so that goes to 0. So actually, I know what happens here. This is, yeah, x to the minus 1 goes to 0, so this is what we've got. So in the end, this is 1. And then we have to remember that that's actually natural log of L. So L is e to the 1. In other words, it's just e. It's kind of crazy when you think about what we just did. A lot of people would say that 1 to the infinity is just 1 because you're multiplying 1 by itself over and over again. But that's kind of, well, that's, well, we just saw an example where it isn't true, because you're not really multiplying 1 by itself over and over again. Again, you have to think this is a function that's going to 1. So imagine that it's a number that's not quite 1, but it's very close to 1, and you're multiplying it by itself a large number of times. It can get pretty big. In fact, this one turned out to E, which is like 2.7. Anyway, so going back to the big list, I didn't do infinity to the 0, but that's just like the others. It's the same natural log L trick, which leaves this last one. So this last one, it's hard to give advice for. They're all different. One suggestion is to use algebra, and it depends what we're talking about. Like, what are these two functions? Like, there's f of x minus g of x, and it depends. You know, sometimes you can simplify f of x minus g of x. In general, anything goes. I mean, anything as long as it's correct, right? It's hard to give advice, or it's impossible to give advice that's going to work all the time on infinity minus infinity. It just depends on what you're looking at. But I'll do an example. Let's take a look at this one. And indeed, this one is infinity minus infinity, because x is going to infinity, so this thing is going to infinity, and of course the square root of, roughly speaking, the square root of infinity is infinity. Like if I take the square root of a larger and larger number, it just grows beyond any bound. And so this part's going to infinity, and then I'm subtracting x, which is also going to infinity. So this is an infinity minus infinity form. So I am going to use algebra. And this is kind of a throwback to some of the tricks we used in Calc 1. I'm going to make this into a fraction. And I'm going to multiply the top and bottom by the same thing. And what I'm going to choose to multiply by is called the conjugate. Let me use parentheses here. The conjugate is, I'm just going to replace this minus with a plus. Whoops, forgot to actually do the conjugate. So it's that. Multiplying the top and bottom by the conjugate is a trick that often works when you're dealing with square roots. That's what clued me in, I would say. And of course, what we're always using, we're using the fact that a minus b times a plus b is a squared minus b squared. And this is what I have. It's like this is my a and this is my b. So I've got a minus b, and the conjugate is, of course, a plus b, because the way we got the conjugate is switching the minus to a plus. So multiplying this out is easy. It's going to be a squared minus b squared. So I'm going to square this. This is my a. And when I square this, the square root just goes away. So that's my a squared. And then I'm going to subtract b squared. And b is just x. So I'm like that. And on the bottom, I'm just multiplying by 1. So I'm there. Okay, let me take a look at what's going on now. Of course, that happens. So now I've got a 2x, and I'm going to divide it by this stuff. So this is actually, this is an infinity over infinity form, right? Because x is going to infinity, so 2x is going to infinity. Also on the bottom, this is like the square root of infinity, so in other words, it's going to infinity, and I'm adding infinity, so infinity plus infinity is infinity. So, yeah, I could use L'Hopital's rule on this, but I don't think that I want to. Because I'm not very excited to take the derivative of this and then have to deal with whatever I get. Like, this would require the chain rule, and I think it's going to turn into a bit of a mess. So you don't have to use L'Hopital's rule just because it's an infinity over infinity form. I'm going to use more old school methods. Let's use algebra. I would like to, how to explain what I'm doing. I want to pull out a power of x from the bottom. There's a power of x on the top too, but that's very simple. Like, it's sort of silly to talk about pulling out a power of x. It's right there. I would like to pull out a power of x on the bottom though. In particular, the square root. So what I'm going to do, I'm going to pull out the biggest power of x that I see. So I see an x squared. Of course, if it comes outside of the square root, x squared becomes just x. And so what happens? When I say I'm pulling out an x squared, that's like dividing this inside by x squared. So x squared just becomes a 1, and 2x becomes 2 over x. That's what happens if I pull an x squared out of a 2x. I get 2 over x. Okay. I can cancel an x from the top and the bottom now. And I have to be careful to cancel it off of everything. So this x is going to be gone. This is going to be gone. This is going to be gone, and it becomes a 1. So this step is probably not quite necessary. But what's left over is this. Just to be clear, this is this 1. It doesn't just disappear. It turns into this 1. Finally, I'm good to go, because as x goes to infinity, this goes to 0. So I'm getting 2 over... This is now just square root of 1. So I've got 2 over 2, so I just get 1. So this is another slightly bizarre situation where, going back to what we were doing, this is like a really big number as x goes to infinity. This is some huge number. And this is some other huge number. And what we just determined, roughly speaking, is that as x goes to infinity, this huge number is approximately 1 bigger than this huge number. Because when I subtract them, and as x goes to infinity, when I subtract them, I get 1. In other words, once again, this huge number is approximately this huge number plus 1. They're just 1 apart. They're both going to infinity, but they stay within 1 of each other.